Welcome to the Deep Dive. Today, we are strapping in for a fascinating journey. We're going to the coldest, emptiest, and weirdly, most chemically active places in the entire universe.
We're talking about those vast, dark clouds you see between the stars?
Exactly. These are the ultimate cosmic laboratories. And our mission today really is to understand the incredible slow-motion chemistry that's happening inside them.
And when you say slow motion, you really mean it.
Mm.
But this is the deep dive into the birthplace of, well, everything that matters. It's the origin story of stars, of planets, of water.
And crucially, the basic organic scaffolding that you need for life itself.
Right. And this isn't just theory anymore, which is the exciting part. We are, for the first time, seeing the actual chemical process unfold, and that's all thanks to the James Webb Space Telescope.
It really is. And our guide through all this dense, rich material is the work of a leading astronomer, Ewine van Dishoeck.
She's fantastic, a world-renowned chemist and astrophysicist who studies molecules in space.
But she's not just an observer. She actually played a huge role in developing a critical piece of the instrumentation aboard Webb, which we'll get into.
So our core material today is really focused on the revolutionary data that's coming from Webb's instruments. And, how scientists are combining those observations from space with really specialized lab work here on Earth.
It's that combination that's so powerful.
It is, and it's all aimed at answering this one fundamental question. What is the universe's recipe for building a habitable world?
And we are definitely going to use that cooking analogy today because it just works so well at grounding these, really abstract concepts.
That's the perfect analogy.
So if you think about exoplanets as the finished cake, ready to come out of the oven, this research is giving us the detailed step-by-step instructions.
And maybe most importantly, the exact ingredients list.
Yes, we're starting right at the very beginning, gathering the raw materials out there in interstellar space.
That starting point it's truly extraordinary. And frankly, it's completely alien to our experience. We're talking about these huge, dark molecular clouds made of simple gas, dust, and ice.
And they just hang out for millions of years?
Pretty much this material just mingles, essentially undisturbed for millions and millions of years, patiently waiting before gravity finally takes over and kicks off the much more chaotic process of star formation.
When you talk about these dark clouds, I think we really need to stress just how extreme that environment is. It's not just cold. It's a level of cold that's, well, it's almost impossible to imagine here on Earth.
It is the deep freeze of the cosmos. These clouds are far, far colder than anything that happens naturally on our planet's surface.
What kind of temperatures are we talking about?
We're discussing temperatures that register below minus 400 degrees Fahrenheit.
Wow.
They often settle just a few degrees above absolute zero, the theoretical coldest possible temperature. And this extreme cold is absolutely essential.
Why is that?
Because it slows down the molecules and allows them to stick together, which is really the very first step in the whole recipe.
Okay, so the cold is one half of the extreme condition, but the other half is the vacuum. And this is where I think the context gets really mind-bending for anyone used to, Earth-based physics.
The vacuum is almost perfect. I mean, when astronomers talk about space, even in what they call a dense region, they mean something that is, for all intents and purposes, empty.
Right.
And scientists on Earth, they have to try to replicate these conditions to model the chemistry. But here's the crucial part, the caveat.
Okay.
Even the absolute best ultra-high vacuum laboratory we can create on Earth, it's still a million times denser than what an astronomer calls a dense, dark cloud in space.
Wait, say that again? A million times denser.
A million times.
That scale is it's unbelievable. So if our Beth lab is that much denser, how does that affect how molecules behave? How do scientists even interpret their lab experiments then?
Well, it dictates the entire chemical process. It's the whole ballgame. On Earth, in a liquid or even in a gas at atmospheric pressure, molecules are constantly colliding, billions of times a second.
And that's what drives chemistry as we know it.
Exactly. That rapid collision rate drives standard chemistry. But in the deep vacuum of interstellar space, even in those dense regions, collisions are incredibly rare events.
So if they're not colliding very often, how does any chemistry happen at all? It seems like it shouldn't.
It happens incredibly slowly. That's the first thing. We're talking time scales of hundreds of thousands of years for a reaction that might take seconds in a lab.
Okay, so time is the key.
Time is one key.
Yeah.
But more importantly, it requires surfaces. The atoms need a place to sort of meet and grate.
A gathering place.
That's it. And that is the role of the dust grains, which we'll talk about a lot more. If you don't have that surface and you don't have that patient cosmic timescale, the complex molecules we're looking for, they simply cannot form in a gas phase.
So that's why you can't just take a lab result at face value. You have to translate it. Hours in the lab versus eons in space.
Precisely. Understanding that difference is absolutely critical.
That context is, yeah, it's vital. Okay, so now let's look at the person who really bridged that gap between, Earth-based chemistry and this cosmic astrophysics. Ewine van Dishoeck. She didn't start out looking at the stars.
Not at all. She started her career studying theoretical and quantum chemistry. So she was dealing with the deep physics of molecules and chemical bonds right here on Earth.
Just trying to understand how molecules react at the most fundamental atomic level.
Exactly. Her initial trajectory was not pointed at space at all.
And the sources tell this really wonderful story about how she made that radical shift. It wasn't some sudden epiphany looking through a telescope.
No, not at all. It was actually a piece of advice from her then-boyfriend, who's now her husband. He was studying astronomy.
What did he say?
He just pointed out that, molecules exist in space, and someone needed to figure out what they were and how they got there. It was a simple observation, but for her, it was this massive intellectual opening.
She realized the space between the stars was, and this is her quote, a fantastic chemical laboratory.
Completely unlike anything she could study on Earth. For quantum chemists, this near-perfect vacuum offered these complex, really exotic reaction pathways. It was just far more intellectually stimulating than her Earth-based lab work.
And she never looked back?
Never. And that transition she made from the microscopic theoretical world of quantum physics to the macro observational world of astrophysics, it shows you exactly why this research is so successful now. You need both. You need the chemical insight and the ability to build the tools to see it across these immense distances.
Okay, let's move from the chemist to the tool itself. We have the cosmic lab, we have the strange conditions, and we have the scientific mind ready to study it. The key that unlocks the door to all this darkness is, of course, the James Webb Space Telescope.
Webb is. It's genuinely an unparalleled scientific instrument. And its power comes primarily from its unique vision in the infrared spectrum.
Right, this is light that's invisible to the human eye.
Totally invisible. But it's the light that can cut right through the dense material in those dark clouds.
So if you think of those dark clouds as being too thick for regular visible light to get through, the infrared acts like a keyhole, right?
The perfect way to describe it. Think of those clouds as a thick, smoky haze. Visible light just bounces off the dust, it gets scattered, it gets obscured. You can't see inside.
But infrared can.
But infrared light, which we perceive as heat, has longer wavelengths that can effectively pass through all that dust and gas. And this allows scientists to peer directly inside, right into the nursery where star and planet formation is actively happening.
And they can measure the heat and the specific chemical signatures being emitted from in there.
Exactly. And as we touched on earlier, the analysis requires taking that data from Webb and synthesizing it with lab work back on Earth.
That still seems like such a massive leap of faith. You're trying to connect a cosmic snapshot, which is the result of eons of chemistry, to a reaction you cook up in an afternoon.
It's a necessary leap, but it's one that requires really rigorous scientific scaffolding. Webb gives you the endpoint. It shows you the result of hundreds of thousands of years of chemical reaction.
And the lab gives you the process.
The lab lets you isolate specific variables like temperature, energy input, reaction partners, and you can observe known chemical behaviors over a controlled short timescale. By carefully extrapolating the rates and products you see in the lab, you can build accurate models of that slow-motion chemistry in space.
So it's essential for figuring out the actual mechanisms of how the molecules form.
That's right. Without the lab work, the Webb data is just a list of ingredients with no instructions.
Speaking of mechanisms, let's focus now on the specific instrument that Van Dishoeck helped champion, MII, the mid-infrared instrument. Why was it so important to have a mid-infrared view when 3 other instruments on Webb already focus on the near-infrared?
This is a really critical distinction that I think often gets overlooked. Webb's whole suite of instruments is designed to cover a broad spectrum of infrared light, but MIRI is special. It's special because it covers the longest wavelengths, the mid-infrared range, specifically between 5 and 28 microns.
And what does looking at those longer wavelengths let MIRI see that the other near-infrared instruments would miss?
It's all about molecular vibration.
Okay.
Different molecules absorb and then re-emit light at very specific, unique wavelengths. It's like a chemical fingerprint. Near-infrared light tends to be absorbed by The fundamental vibrations of really simple molecules like hydrogen or carbon monoxide.
The basic stuff.
The basic stuff. But
Yeah.
mid-infrared light is crucial for detecting the more complex vibrational modes of heavier molecules, especially the complex organic molecules that contain multiple atoms, the really interesting building blocks like simple sugars, alcohols, and silicates.
So if you want to find the complex organic precursors, the most interesting ingredients for our cosmic cake, you must have that mid-infrared view that MRI provides.
You absolutely must. It's the key. It significantly expands the chemical inventory that you can detect. And MIRI doesn't just capture images.
Which it does spectacularly. I've seen that image of the Herbig-Haro 4950 outflow with those intense reddish-orange bow shocks. It's incredible.
It's a stunning image.
Mhm.
But MRI also collects spectra.
And for the chemists, the spectra are the real gold mine.
They are the detailed printouts. A spectrum breaks down the light into all its constituent wavelengths, and that gives you a detailed fingerprint of the specific molecules that are present. So if the image shows you where the chemistry is happening, the spectrum tells you what chemistry is happening.
It's the precise list of ingredients in the cosmic pantry.
Exactly.
But to get those spectra required, well, one of the greatest engineering feats of the entire project, we already established that Webb needs to be cold, but MIRI needed to be exceptionally colder, right? To stop its own heat from just washing out the signals.
It's an insane challenge. I mean, think about it. Infrared light is heat. So to measure these tiny heat signatures from objects millions of light years away, your detector has to be way, way colder than the signal you're trying to measure.
And the rest of the telescope uses that giant sunshield to cool down passively.
Right. The rest of the telescope gets down to around 40 Kelvin, which is already incredibly cold.
Yeah.
But MIRI needs to be below 7 Kelvin.
Below 7 Kelvin. How do you actively refrigerate something a million miles away in deep space? It sounds like something out of science fiction.
It basically is. It required inventing entirely new technology. MIRI has its own dedicated two-stage special refrigerator called a cryocooler.
A cryocooler.
The first stage gets the instrument down to about 18 Kelvin. But then the second critical stage uses this tiny, precisely controlled flow of high-pressure helium gas in a closed-loop system. The gas is then allowed to expand, and that process of expansion naturally pulls heat away from the detector housing. It's an incredibly delicate process.
And this system has to maintain a constant, steady temperature of less than 7 kelvins. That's what, barely 4 degrees above absolute zero, minus 447 degrees Fahrenheit.
Something like that, yeah.
What happens if the temperature drifts even slightly?
It blinds the instrument. That's it. This extreme precision is necessary because the detectors themselves are incredibly delicate. They're built using a specialized formulation of arsenic-doped silicon, or SiEyes.
Okay, why that specific material?
Well, for the learners out there, the core reason is that this material has an extremely low band gap energy. At even slightly higher temperatures, the electrons in the silicon would gain enough thermal energy to just jump across that small gap on their own.
And that would create electrical noise.
A huge amount of noise. It would completely overwhelm the faint signals coming from distant space. It would be like trying to listen for a pin drop during a rock concert.
So the detection of complex cosmic chemistry literally rests on the successful operation of a refrigerator and detectors built from these custom-invented materials, all working perfectly a million miles from Earth.
Precisely. And this whole struggle to get MIRI included and functioning, it was a decades-long effort for Van Dishoeck and her team.
Let's expand on that a bit. She started working on this back in the late 1990s. What was it that motivated her to fight so hard for a mid-infrared spectrometer when the whole Webb project was already facing so many technical problems?
Her motivation came directly from the data from the instrument that came before it. The European Space Agency's Infrared Space Observatory, or ISO.
That was back in the mid-90s.
Right. And ISO showed them that the infrared spectra of these star-forming regions were incredibly rich. They were far more complex than anyone had anticipated.
So they got a little peek and realized the most important part of the story was hiding in the mid-infrared range.
Absolutely. The ISO data proved the potential, but the spectra were noisy, they were limited, you could barely make things out. So Van Dishoeck and her small group of scientists had to push and push hard to make sure that Webb didn't just include a mid-infrared camera, but a proper, high-quality spectrometer.
One that could get the chemical fingerprints they needed.
Exactly. They knew they were fighting against budget constraints, engineering constraints, everything, but they just saw the absolute scientific necessity of it.
And after 2 decades of development, the agonizing wait didn't stop at launch. She described the months after the launch as just immensely stressful, just waiting for MIRI to finally cool down.
That moment was absolutely critical.
Yeah.
The engineers had done their job getting this complex cryocooler into space, but the big question was, would it actually work? Would it perform this delicate low-temperature function? She talked about watching the live webcam feeds, just anxiously waiting for the temperature to drop below that 7 Kelvin threshold.
I can't even imagine the relief.
Oh, it was an enormous relief for everyone involved when MIRI finally achieved and stabilized its operational temperature.
And the data payoff. It must have made all those years of fighting for it worthwhile. How did those first spectra compare to what ISO or even the Spitzer telescope had delivered before?
The comparison was, it was revolutionary. Van Dishoeck described the data from the previous instruments as having tiny little wiggles.
Tiny little wiggles.
Yeah. It was, suggestive evidence of a molecule. You thought something might be there, but you couldn't be certain.
Okay.
When the first MIRI spectra came in, those tiny little wiggles transformed into booming lines. Just huge, clear signals that were instantly identifiable.
That's incredible. So you go from suggestive evidence to absolute certainty. That must completely change the pace of discovery.
It does. It confirms the inventory, and that allows the chemist to move on to the next step, which is understanding the mechanisms.
It just eliminates all the ambiguity.
It's the difference between trying to read a blurry handwritten note with half the letters missing and reading a perfectly typeset ingredients list.
That is a perfect segue back to our recipe analogy. We have the instrument. Now let's gather those ingredients. Step one in making this cosmic cake happens in those super cold, collapsing dark clouds.
The key mechanism here is a process called freezing out.
Freezing out.
Yeah. The atoms and simple molecules that are just floating around in the gas phase, like hydrogen, oxygen, carbon, they randomly collide with the surfaces of these tiny cold dust grains.
And because it's minus 400 degrees, they don't bounce off. They stick. They build up an icy mantle.
Exactly. Think of those dust grains, which are just a fraction of the width of a human hair, as the first little collection vessels. The gas atoms land on the surface, and they just become fixed there, forming this icy layer over time. It's like the really dense ice that builds up on your car windshield during a massive winter storm.
What are the first layers of that cosmic ice made of?
Well, the deepest and most abundant layer is frozen water ice, H2O. After that comes carbon monoxide ice, CO, and carbon dioxide, CO2.
And Webb can measure the ratios of these ices.
With incredible precision. Using MIRI, it can measure the exact ratios in different systems, which tells us how much oxygen and carbon is available right at the start. But the really exciting part is what happens next, on the surface of those grains.
Right, the chemistry on the surface, that's the kitchen counter where the new compounds are getting mixed.
That's it. These dust grains are acting as reaction sites. They're surfaces. Because collisions in the vacuum are so rare, the only way for simple atoms to meet and bond to form more complex molecules is if they're both stuck together on the same grain surface.
And then they can sort of move around on that surface until they find a partner.
Exactly. They can migrate across the surface.
But wait, doesn't the extreme cold also inhibit chemical reactions? I always thought you needed energy, heat, to get molecules to combine.
You do, but the universe is clever. This is where we get into some more exotic mechanisms. In the gas phase, yes, you need a lot of energy to overcome reaction barriers. But on the surface of these cold grains, chemistry can happen through other means.
Like what?
Like UV photolysis, where a stray ultraviolet photon from a distant star provides just a tiny energy boost. Or, and this is fascinating, through quantum tunneling.
Quantum tunneling. That sounds like something only theoretical chemists should be talking about.
It is. But it really happens in space. Because the atoms are so light, especially hydrogen, and the temperature is so low, they don't need to physically jump over the energy barrier to combine.
They can just appear on the other side.
Statistically, yes. They can tunnel right through the barrier. And this turns out to be a highly efficient way for simple atoms like hydrogen and oxygen to combine even at these ridiculously low temperatures to form larger compounds like water ice and eventually more complex things.
So that patience and that extreme cold and this quantum weirdness is what allows for the formation of the ultimate ingredient for life, water.
And this is a massive discovery that Webb has now confirmed. The majority of the water that we find in future planetary systems, it isn't formed later on when the system gets hot.
It's inherited.
It's inherited. It forms much, much earlier on those small dust grains during this cold, quiet phase of cloud collapse. Long before the star even fully ignites, it's been locked away in that ice mantle the whole time.
And MRI spectra are showing that the ingredients list is a lot more sophisticated than just frozen water and CO2.
Oh, dramatically so. The detail Webb provides is exquisite. It's allowing scientists to identify not just the simple stuff, but molecules that act as critical organic precursors.
What kind of things are we talking about?
We're talking about methanol, which is a simple alcohol, even more structurally complex molecules like acetaldehyde, and in some of the most exciting detections, simple sugars, and even simple alcohols like ethanol,
Ethanol, like drinking alcohol.
the very same molecule.
So these are the early building blocks that bridge that gap from basic water chemistry to the complex molecules you need for biology.
Exactly right. These organics get incorporated into that icy layer. And later on, when this ice gets incorporated into comets and asteroids, those objects become the essential delivery mechanism.
Yeah.
They bring both the water and this rich organic material to the surfaces of new forming planets.
So the chemistry of life is literally baked into the initial dough of the system.
A perfect way to put it.
We can even see this transition from the quiet chemistry to the more energetic phase in the visual data. Let's go back to that observation of Herbig-Haro 4950.
That image is a visual feast, and it confirms the sheer energy of starbirth. When the protostar at the center finally ignites, it doesn't just, quietly turn on like a light bulb. It ejects these powerful, fast-moving jets of material.
And in Herbig-Haro 4950, we see these intense reddish-orange bow shocks, these arc-like features that look exactly like the wake of a speeding boat hitting the water.
That visual represents the moment when all those cold, patient ingredients are violently disturbed and activated by the young star's energy.
And the spectra confirm what's happening chemically.
Yes, as those jets slam into the surrounding material, the friction and the shock waves heat up the ice mantles on the dust grains and releases all those stored chemicals back into the gas phase. Scientists are detecting a complete chemical zoo in those ejections.
Things like carbon monoxide, water.
Water, methanol, and all sorts of other shock-activated organic compounds. It's like the pantry door's been blown open.
So we have the complete ingredients list stored in ice, enriched with organics, and we have the high-energy processes that are starting to stir the mixture. So now for the next step in the recipe, turning those microscopic dust grains into actual planets.
Okay, so star formation, as we discussed, starts with that vast cloud collapsing under its own gravity. This heats up the inner region where the new star forms, but it leaves this massive rotating disk of material surrounding the protostar.
And the precise mechanics of how a system like ours gets built from that rotating disk of dust and gas, that's still one of the deepest questions in all of astrophysics, right?
It really is. The process starts microscopically, with those dust grains that are a fraction of a hair's width. They collide, and because of surface physics and the presence of all that ice, they stick together. They build up like cosmic snowballs.
So they grow from dust grains into pebbles, then into rocks?
Yes, and crucially, they eventually grow into what astronomers call planetesimals. These are robust kilometer-sized bodies. Think of a large comet or an asteroid.
And these planetesimals are the fundamental building blocks.
They are. If you can aggregate enough planetesimals together, you can build a core that can then gravitationally track the surrounding gas, and boom, you end up with a planet.
I remember when the whole concept of these rotating disks was pretty much theoretical. Have our modern telescopes confirmed that these structures are common?
Oh, absolutely. The idea of gas and dust disks around young stars, it was only convincingly imaged for the first time in the 1990s. Now we can see them in stunning detail. And that's thanks to a tag team approach with our instruments.
Ah, so this is where Webb needs a partner telescope to really complete the visual story.
Yes, exactly. This is where we bring in the Atacama Large Millimeter Array, or ALMA, which is located in Chile. ALMA is brilliant at imaging the millimeter-sized dust particles in these disks. It's given us the most beautiful high-resolution images of the physical structure of these disks, showing they're typically the size of our own solar system.
And what those ALMA images showed was that these disks are far from being, smooth, uniform, spinning plates of dust.
That's the key insight. They contain incredibly complex structures. We see these vast gaps and cavities that are almost certainly being cleared out by young, newly formed planets or planetesimals that are orbiting the star.
Like a snowplow clearing a path.
A cosmic snowplow, exactly.
Mm-hmm.
We also see spiral arms, bumps, and critically, these areas known as dust traps.
Dust traps. That sounds like a pretty necessary mechanism for planet formation. How do those structures concentrate the material?
A dust trap is essentially a pressure maximum within the gas disk. Dust grains and pebbles, which are the planetary building blocks, they tend to orbit at slightly different speeds than the gas itself. When they encounter this pressure maximum, they get slowed down and they accumulate there.
So they act as massive storage areas for potential planetary cores.
That's it. This solves a major puzzle in planet formation. How do these small grains avoid just spiraling into the central star before they have enough time to grow into large planetesimals? The dust traps save them.
So LMA shows us where the blocks are accumulating. Now let's bring Webb back into the picture. What is Webb revealing about the chemical composition inside those massive building block regions?
That's where it gets really exciting. Webb is revealing an incredible and frankly surprising richness of molecules in these disks. And it's leading to what scientists are calling a profound chemical dichotomy. This is one of the hottest new areas of research.
A chemical dichotomy. So you're saying there are two distinct types of planetary systems being revealed.
It seems so. On the one hand, we have disks that are extremely rich in water molecules, not just ice, but water vapor and highly oxygenated compounds. These systems look like clear precursors to solar systems like our own. They're promising rocky, water-bearing planets in the habitable zone.
Okay, that makes sense. But what about the surprise? The carbon-rich disks?
This is the curveball. The second type of disk is extremely, almost aggressively rich in carbon-containing molecules. These disks have very little detectable water, which suggests the water has either been locked away differently or it just wasn't as abundant to begin with.
But they're booming with carbon compounds.
Booming is the right word. MIRI spectra are detecting massive amounts of molecules like acetylene, which is a simple hydrocarbon, and even more surprisingly, highly complex molecules like benzene.
Benzene, that's a ring structure. That means highly sophisticated, complex organic chemistry is still actively happening in the inner, hotter parts of these young disks.
It does. Benzene, C6H6, is a precursor to what are called polycyclic aromatic hydrocarbons, or PAH. Its detection strongly suggests that the chemistry in these carbon-rich environments is going down a path that is fundamentally different from the water-rich systems.
And we don't fully understand this carbon-dominant chemistry yet.
Not at all. But it could influence the resulting planets in some really dramatic ways.
Are we talking about the potential for, like, exotic planets? Carbon planets where the interiors might be dominated by graphite or even diamonds?
That is the potential implication, yes. If a disk is highly enriched in carbon relative to oxygen, the rocky planets that form there would likely have a composition dominated by carbon-based minerals, not the silicate-based minerals we see on Earth.
Which could lead to some very interesting diamond-rich geologies.
It could indeed. What Webb is telling us is that the universe seems to be building planetary systems on at least two distinct chemical recipes, one that's water-based and one that's carbon-based.
This incredible chemical inventory inevitably takes us to the ultimate pursuit of all this research, the astrobiology connection, the search for life beyond Earth.
It really is the driving force. It's behind the funding, it's behind the public interest. Webb's research is fundamentally about assessing the basic ingredients necessary for life as we know it, which of course requires water and organic precursors.
And based on all the evidence we've just discussed, the cosmic pantry is fully stocked.
Overwhelmingly so. Webb has confirmed that water is abundant in nearly every forming star system and disk that's been surveyed. And the basic organic material precursors, alcohols, sugars, hydrocarbons, they are also clearly available and readily synthesized in that cold environment. The universe is not short on ingredients.
But our guide here, Ewine van Dishoeck, draws a very sharp and I think necessary line in the sand. She separates her field from biology.
She does, and it's a crucial limitation to acknowledge. Provided the ingredients, confirming the presence of water and organics, that is the job of the astronomer and the chemist, the actual profound mystery is the puzzle of assembly.
How to take those basic building blocks and transform them into the first functioning, replicating cell.
Exactly. It's the difference between delivering a box full of disassembled Lego bricks and figuring out the complex instruction manual required to build the first functional structure.
That's a great analogy.
That leap from a complex molecule to a basic biological system is a problem for organic chemists and for biologists. We can confirm the environment is stocked, but the steps required to go from benzene and methanol to self-replicating DNA. That is still a profound, unknown leap that happens way outside the scope of current astronomical observation.
And that separation of problems really defines the path forward for the search for life, doesn't it? If we're looking for actual biological signatures, this research provides the foundation, but the final detection is going to require new tools.
It does. And van Dishoeck is appropriately conservative on the timeline for finding life. She's clear that finding actual biosignatures, gases in exoplanets' atmosphere that definitively prove a biological process is underway, that will likely require new specialized instruments and dedicated missions that go beyond JWST.
But every piece of data Webb gathers is crucial for identifying the most promising candidates to point those future instruments toward.
That's the goal. We're building the roadmap.
When you dedicate decades of your life to solving questions this big, there must always be these lingering points of personal curiosity. What does Van Dishoeck still obsess over, even with all this incredible data that MIRI is providing?
She shared a few wonderfully specific, chemist's curiosities. Despite all the spectroscopic confirmation, as a quantum chemist, she remains intensely curious about the fundamental details of how those atoms actually manage to come together on the grain surfaces.
Even to form the simplest molecules.
Even the simplest ones. We have models of quantum tunneling, but she wants more direct observational evidence of those microscopic reaction pathways.
The need to see the mechanism in action, not just the final result.
Precisely. And then beyond the molecular level, she's deeply focused on putting our own Earth into context.
Yeah.
She asks the big questions. What made our planet the way it is? Was the ratio of water to carbon that formed Earth something special, or is it common?
It's the quest for planetary self-awareness, really, using the universe as a control group to understand ourselves.
I love that framing. That's exactly what it is.
And then there's the delightful science fiction wish that kind of ties into that need for direct data.
It's the scientist's ultimate fantasy, isn't it? She confessed she's still from the Star Trek generation, and her deepest personal wish would be to serve as a science officer on a starship.
Her job.
To be able to physically travel to a place like the famous Orion Nebula, take a literal scoop of the material, a physical sample of the cosmic recipe, and study it in great detail right there in the lab on the ship.
That desire for a scoop of material just perfectly encapsulates the scientific challenge. We're interpreting light from millions of miles away to understand chemical composition, when the ideal scenario would just be a direct measurement.
And that desire is what drives the future of instrumentation.
Before we transition out, let's take one last dramatic look at the sheer violence that defines these stellar nurseries, which is just so beautifully captured in Webb's imagery.
Yeah, we can look at the image of the Pismas 24 star cluster. It's situated within the vast Lobster Nebula, and Webb's detectors show us these incredible gold and orange newborn stars. And these are not modest, quiet stars like our sun.
They're huge.
They're massive and intensely hot. Some of them are 8 times more luminous than the sun.
And their sheer power demonstrates the destructive side of starbirth.
Absolutely. Their intense radiation and their powerful solar winds carve out these massive cavities and aggressively shape the surrounding gas and dust clouds. And that results in those jagged, ethereal peaks we see in the images. Starbirth is a destructive process that rips apart and illuminates the very clouds that provided its initial chemical ingredients.
And in doing so, it redistributes the contents of that recipe throughout the galaxy, making sure the next generation of stars has its starting materials.
Exactly. It's the ultimate cosmic recycling program.
So we have covered the entire cosmic recipe, from the quantum tunneling that freezes atoms onto grains in the deepest cold, to the formation of chemically distinct carbon-rich and water-rich disks, all validated and confirmed by the incredible vision of the James Webb Space Telescope.
And the core realization here, the thing that really informs the search for life, is that Webb's instruments allow us to watch this formation process in stunning chemical detail. We are proving, system after system, that the essential chemical ingredients for life water and organic precursors are readily available. And they're formed extremely early in a stellar system's life.
So the cosmos is structurally and chemically prepared to host life.